We come to the last aspect of vertical climb, vertical descent and hover. So now we are going to look at what happens when a helicopter is vertically descending. You may wonder, why would it want to vertically descend? Perhaps you are trying to land on top of a building and you want to position yourself above the building, then descend down. Or perhaps you have a clearance in the middle of a woods or a forest where you have to vertically descend. Or you may be doing a crane operation where you are doing lifting and loading and unloading material and you need to vertically move up or down. You may also get a situation where you don't have any power. Suddenly you lost the power and you don't want to keep forward in forward flight and descend. Because of operational constraints, you are required to vertically descend. So what happens aerodynamically? So this is what we are going to be looking at this module. Unlike all our previous modules, this would be more of a qualitative discussion, not a quantitative discussion. So why is that? Because when you're descending, you can use your potential energy as one of the sources of power. Therefore, even if you lose engine power, you do have the source of power. There are really two sources of power. One is the engine blade rotating, kinetic energy in the blades. But you don't want the blades to come to a stop. You want them to keep spinning. The second source of energy that you have available is your potential energy. So we are not worried so much about the power considerations. We want to know physically what's going on, what are the difficulties, and how can I estimate, for example, the rate of descent for a given vehicle at a given weight. So as I mentioned to you, these discussions are going to be qualitative rather than quantitative. And we will use a momentum theory, which is the actuator disk model, as the primary model to guide our analysis. We already saw that the actuator disk theory is very crude, very approximate. Therefore, this is going to give you only a rough guideline of what's going on physically. So let's start looking at the power needed in climb and hover from the actuator disk model. This is an equation that we have seen earlier. In this equation, P is purely the induced power. First term is T times V is the thrust, which is the weight of the vehicle, times the rate of climb. So you could think of this TV as the energy rate at which you are increasing the potential energy. Every second you are climbing to a certain altitude. So rate of climb times T is the rate of change of potential energy. So that's the first term. The second term is T times a lowercase v is the induced power, because you are pushing the molecules down. They have a higher velocity compared to what they started with. So the kinetic energy that you expend in the molecules is per unit time is the induced power. So taking the closed form expressions from the actuator disk model for the induced velocity lowercase v, adding it to uppercase V, which is the climb velocity, you get an equation that looks like this. So you will see the curve, if you plot it, climb velocity versus this particular power, you'll have a curve as shown in here. Asymptotically, what would happen is at very, very large values of capital V over 2 would be much larger than T over 2 rho A. That means the climb velocity is much higher than the induced velocity. Then the power will behave like a P equal to TV, will behave like a linear curve. Okay. So that's what's happening here. So if you look at the particular thing, we're going to this slope will become a 45-degree slope. So you can actually draw a straight line with 45-degree slope. So this curve will be tangent to that straight line, P equal to 3V at a very, very high altitudes. Now this model does not work so good in descent. Remember, in descent, you're losing altitude. So if climb velocity is positive, descent velocity is negative. So if you put a negative number for V here, Notice that this number is always higher than this number. So you're going to get a power equal to always a positive number. Therefore, no matter how rapidly you descend, you're always going to get, you're going to require power. So that's what's shown in the next picture here. So when you descend, so this is the relationship we get when you descend. Notice that this number is always positive even when V is negative. Therefore, no matter how rapidly you descend, you still need power supplied to descend. It doesn't make sense. We know helicopters will fall like a rock when they are vertically descending. So why do we need to supply power? Because you have all this potential energy available. So this equation is something is wrong with it. Okay. So mathematically, we immediately see something is missing in vertical descent. If you simply blindly apply the blade element theory or the actuated disk theory based model to the power. You could also get some idea physically what's going on by looking at this picture here. So let me switch back to the full screen. So on the left side, you see the traditional vertical climb case. Everything is downwards. Capital V, far above the rotor disc, is down. Capital V plus V through the rotor disc is down. V plus 2V is down. Because V is down, induced velocity is positive, but it's pointed downwards. And the climb velocity is down. So everything is pointing in downwards. So it produces a physically acceptable behavior. Although we see there's a discontinuity in the downward directed velocity in the far wake, because outside the wake it's a V plus, just capital V. Inside the wake it's V plus 2V. So we produce some kind of a shear layer. Basically the vortex rings that are coming down from the rotor, they form like a shear layer like structure. So it can be visually observed in a lot of experiments. Now, if you use the same principle or the same actuated disk model to the climb, then what happens is outside the rotor disc, capital V is up now. That means because you're descending. Far above the rotor disc, capital V is up. But at the rotor disc, capital V plus lowercase v is down. So something is discontinuous. What's going on? Also, in the wake, if you see it, in the far wake underneath the rotor, you get a very large discrepancy because one is going up, the other one is coming down. Very large values of shear stress, a shear rate, or a vorticity, which is not consistent with physics. So we have to modify this model. Well, we modify it, we say we are right now talking in terms of dimensional values. Let's go and non-dimensionalize everything because then it'll apply for not only an actual physical rotor, but also for a scaled model rotor. It's very easy to drop a scaled model rotor and experimentally measure what's going on in vertical descent compared to a full-scale rotor. It's less expensive, so we want to non-dimensionalize everything. So we could broaden it, scale it for a large variety of sizes and shapes of rotors. So how do we non-dimensionalize it? We say I'm going to non-dimensionalize all the velocities, including the climb velocity, by square root of T over rho A. That's the inflow velocity in hover. So if you look up here, when capital V is 0, you get square root of T over 2 rho A as the induced velocity. So that's the induced velocity. So we are going to non-dimensionalize all the velocities by square root of T over rho A. That's for the horizontal axis, okay, where we have the velocity, capital V. Now it will become capital V divided by V horizontal. In the vertical axis, we have power, which is T times capital V plus small v. So we are going to non-dimensionalize by T times V hover. Remember, T is just the weight of the vehicle because we're talking about vertical motion up and down, vertical equilibrium. So thrust equal to weight. So if when you do that, your vertical axis now will become capital V plus lowercase v divided by v hour. H stands for hour. So now we are going to look at 3 different scenarios. I'm going to show you what happens physically. They are called progressively, as you progressively descend faster and faster. You'll first go through something called a vortex ring state. Then if you descend even faster, you'll go through a state called turbulent wake state. Then if you descend even faster, then you'll get what you call a windmill brake state. The blade acts like a windmill or a wind turbine. It starts spinning because it's extracting the energy from the oncoming stream. That happens only at very high descent rates. So you have before you get to that windmill brake state, which is a very high descent rate, there's a medium velocity descent, that's a turbulent wake state, very low velocity descent, which is called the vortex ring state. It turns out these cannot be exactly analyzed. There's no closed form solutions, although for windmill brake state, there is some closed form solutions available. Wind turbines, there are a lot of computer programs similar to our blade element theory. I teach a course on wind energy where we develop these. But in the vortex ring state and turbulent wake state, the flow is very unsteady, very chaotic. We can only qualitatively describe, what's going on in these states. So let's look at the vortex ring state first. So here is a vehicle is slowly starting to descend. Okay, not very rapidly, slowly starting to descend. Therefore, outside the steam tube that's flowing through the rotor, all the velocities are upwards. Capital V is up. But capital V is so small, capital V plus lowercase v is still positive, so it's pointing downwards. So you need power. T times capital V plus lowercase v is positive number. Therefore, you need to supply power when you're descending at very, very low speed from the engine. If you don't have engine power, you'll start dropping like a rock until capital V increases, which is the next state. Now, what happens in the wake case? Remember in our previous discussions on vortex wake-based inflow model, we said a helical vortex structure forms underneath the rotor. The helical vortex structure is also contracting, so it's descending, it's contracting. So it wants to be pushed downwards by this quantity V plus capital V, but the upward directed velocity is pushing it upwards. So what happens is these vortices get trapped underneath the rotor disc, forming a donut-like structure. So we call this donut-like structure vortex ring. So inside this ring, here are these tip vortices, and tip vortices are continuously being generated by the rotor. Therefore, this donut ring-like structure will grow in size like a balloon, slowly expands in size. When there's too much vorticity, it'll kind of burst. Some of these vortices will escape outside the slipstream up and above the rotor. Then a brand new, fresh vortex ring will begin to form. Therefore, you have a vortex ring forms, grows, bursts, reforms, grows, bursts. So it's an unsteady situation. When this happens, the vehicle is in a highly unsteady scenario. Pilot or an autopilot will have a hard time controlling it at such low descent velocity because of this unsteadiness. So if you look at how much the power is being supplied by the rotor, you get a scatter because of this unsteadiness. So the blue region, notice that now we are on the left side of the curve. Capital V is negative, so we are descending. The vertical axis is the power needed in descent. So up to a certain descent velocity, roughly around minus 1.71 times VH, you need to supply power. Below that, you still need to supply, you don't need to supply power anymore, at least from the potential induced power consideration. You may need a little bit more power from a profile power consideration, but roughly minus 1.71 VH is where if you run out of power, you can still safely descend down. So you see a lot of scatter in the data for the power, both above the curve, above the x-axis, where you are descending slowly, and below the x-axis. Okay. So this is the vortex ring state. Okay. So again, the left side of the vertical axis is climb. The right side of the vertical axis is climb. The left side of the vertical axis is descent. So we are now looking at the vortex ring state, where these vortices form. They collect underneath like a ring, like a donut ring. They grow in size like a balloon. Then they burst. Some of these vortices escape outside the rotor disk, up and away. Then a new vortex ring forms. Forms, bursts, forms, grows, bursts, forms, grows, bursts. So it's an unsteady phenomenon. So this is called the vortex ring state. It cannot be modeled. Perhaps using CFT, people have tried to model it. But experimentally, it can be measured. Blade element theory would not work. Combined blade element theory would not work. None of the theories we had developed would work. So it's a highly unstable situation. Now let's descend a little bit faster. Now what happens is capital V is up. That means the flow is coming from bottom to top, outside the slipstream, outside the tube of streamlines that are crossing the rotor disc. Now, because capital V is up, even though lowercase v is down, we are still producing induced velocity, pushing the molecules down. V plus capital V is up. So everything is going at the rotor disc above. So the vortices, rather than gathering underneath the rotor disc like we saw in the previous picture here, because V plus V is down, now the V plus V is up, they gather above. Okay. So they collect, a ring-like, vortex ring-like structure forms, they grow in size, burst, some of the vortices slip upwards. So this is still a chaotic situation. Okay. So this is what happens in the vortex turbulent wake state. Why do we call it a turbulent wake state? Because now the rotor disc looks like a bluff body. So capital V is the flow over the bluff body. So these vortices look like the wake behind a bluff body. So if we have a circular disc or a 25-cent coin, if you put it and blow vertically air through it, all around the edge of the coin, it'll form a wake structure. So that's what this looks like. So in this picture, the bottom part of the horizontal axis is the turbulent wake state. Again, it's unsteady. There's a lot of unsteadiness to it. So as you descend faster and faster, this unsteadiness fortunately decreases because these vortices move farther and farther away from the rotor. This donut state ring elongates. Okay. Now we reach a state where capital V is even higher. Okay. So this is the turbulent wake state. Power is now negative. Engine need not supply power. We are underneath the curve. So the potential energy itself is producing the power that you need. The rate at which you are losing the potential energy is what is keeping the engine rotor rotating. Now, when you descend even faster, then you get a situation. Everything is pointing upwards. Capital V is up outside the rotor. So you're descending. So air seems to rush towards you from bottom to top. On the rotor disc, capital V plus lowercase v is up, because even though the induced velocity is pushing downwards, capital V is pushing upwards, the net sum is pointing upwards. Even inside the slipstream, V plus 2V is pointing up. So now those tip vortex structures have a lot of room. They can move up and away. So they don't bunch up either above the rotor disc, like the turbulent wake structure. They don't bunch up below the rotor disc, like the vortex ring state we saw before. You get a nice clean flow. No more forming and bursting of vortex rings. So now we get a steady state solution. So now the thrust is, we can go back to our actuator disc-based model and we can develop a relationship for it. So without formally deriving that particular relationship, I will say that the induced velocity now is minus V over 2 minus square root of capital V over 2 minus T over 2 rho A. The power is, from the sign convention, is now it is negative. So power is negative means we are extracting the power from the air stream as though it is a windmill. So this is what we get from our actuator disk model. Well, how can we explain the power production? Very simple. Look at our typical aerofoil section here. Looks very ugly. Okay. That aerofoil section says in-plane component of velocity omega times r. At every radial location, this velocity is higher or lower depending on r. You have a vertical component of velocity, capital V plus lowercase v. Therefore, total velocity vector is now rotated in the counterclockwise direction. Therefore, the lift vector is rotated in the counterclockwise direction. So one component of lift is pointing upwards, which is what's holding up the rotor that overcomes the gravity. But we see an extra component, horizontal component of the lift vector, that is pushing the rotor, causing it to rotate. So this is causing it to windmill. So the rotor auto-rotates, so at a fixed RPM. Okay. So the rotor keeps on rotating even though you have lost the engine power, because your oncoming air makes your rotor behaves like a wind turbine. Now it turns out that this omega is remarkably constant during this is by the way called windmill brake state, B-R-A-K-E state, not B-R-E-K state where things crash and fail, okay, brake state. Now let's say that your omega drops, okay, for some reason your RPM drops, then omega r, horizontal component, will decrease relative to capital V plus lowercase v. Then the total velocity vector will have a higher clockwise rotation. Therefore, your lift vector will rotate more in the counterclockwise rotation, I should say. Then you'll have a higher forward-directed propulsive force. So this will cause the rotor to spin faster. So increase the omega. On the other hand, let's say you're going at a very, very high omega, capital omega. The opposite thing will happen. The horizontal component of velocity will increase relative to the vertical component of v plus v. Then the total velocity vector will rotate slightly to the clockwise direction. So the lift vector will rotate slightly in the clockwise direction. Then the forward-directed in-plane component of force will decrease in magnitude, slowing down the rotor. So this is remarkably self-stabilizing. Okay. So omega remains stable during the wind turbine brake state when you are vertically descending, and the wind turbine effect is producing or supplying you power. Putting it all together, we have on the right-hand side hover, then climb, that we have seen from our basic momentum theory. On the left-hand side, above the x-axis, you have vortexing state. That's the blue scattered data region. And a little bit of a turbulent wake state underneath as the capital V becomes more negative. As capital V becomes even more negative, then you get a windmill brake state, which is a nice smooth curve. So this is the behavior of the performance map. Okay. Now, the crossover point, which we saw here at the x-axis, is minus 1.71 times VH. Okay. So if you look at the T equal to 1/2 rho A, some effective drag of the rotor, CD, times 1.7 VH, this is the velocity at which you are descending, rate at which you are descending. So 1/2 rho A times the velocity squared is dynamic, 1/2 rho times velocity squared is dynamic pressure, times the disk area A times CD is the thrust. Now if you substitute for VH square root of T over 2 rho A, then T will cancel out, A will cancel out. Then what you would get is an expression for CD equal to, you will get 2 times 2, 4, divided by 1.7 squared, which is 2.89. So this is 1.4. So this is the effective drag coefficient of the rotor when it's in descent. It turns out parachutes, when you test them in vertical descent, parachute with a base area, capital A, remember it's got a dome-like shape, so the bottom of it is a circular shape. So that circular area A is, so the rotor acts like an equivalent parachute. So rotor in vertical descent during the windmill brake state is as good as a parachute. This is why the pilots are able to safely vertically descend, survive, and live to tell the story. So later on in our section on vehicle performance, we are going to revisit this. We are going to talk about more what happens in forward flight, what happens to the RPM of the rotor, does it increase, decrease. We are going to all look at it later on in the vehicle performance section of this course. So right now, to summarize it, in vertical descent, initially you have a vertical climb, then you have a hover, then you have a vortex ring state, then you have a turbulent wake state, then you have a windmill brake state. So these are the various states as you go from a very high capital V in climb to very high negative V in descent. Okay, so this is the stages or phases through which the rotorcraft goes through. So this concludes this lecture, and we will stop at this particular